Thanks again, everyone, so much for joining us for our next GoAERO expert lecture. Um, as always, we're so pleased to have our partners and sponsors, Boeing, NASA, RTX, and many others who are supporting us for our 3-year GoAERO prize, along with our partners and partner organizations all around the world who are supporting us through the entire competition. So today it's my pleasure to introduce you to Dr. Dan Raymer, who is the president of the design and consulting company Conceptual Research Corporation and serves as program manager, configuration designer, and chief engineer for its varied projects. Current and recent projects include the DARPA Flying Missile Rail, the Raymer Manned Mars Plane, and a proprietary high altitude UAV. He is the recipient of the prestigious AIAA Aircraft Design Award. Dr. Raymer is a recognized expert in the areas of aerospace vehicle design and configuration layout, computer-aided design methodologies, and design education. During his 10 years in the advanced design department of Rockwell, he conceived and led the layout design of Rockwell's entries in what became the F-22, B-2, and T-45 programs, and was head of air vehicle design for the X-31 from blank sheet of paper to the configuration that flew. Dr. Raymer is the author of the best-selling textbook, Aircraft Design, A Conceptual Approach, and the well-regarded layman's book, Dan Raymer's Simplified Aircraft Design for Home Builders. His biographical book, Living in the Future, The Education and Ventures of an Advanced Aircraft Designer, covers his career and his design projects. Dr. Raymer received his bachelor's and master's in engineering degrees in astronautics and aeronautics from Purdue, an MBA from USC, and a doctorate of engineering from the Swedish Royal Institute of Technology. It's my pleasure to introduce Dr. Dan Raymer.
Let's see, am I on screen already? Screen sharing?
All set, thank you.
Okay, super. Well, hello, good morning, everybody. And what a fun project that you're all involved in. I am Dan Raymer, and I'm going to be talking about conceptual design aspects of this project, a little bit of background information, sort of a little bit of a mini short course on some material. And in fact, some of the stuff does come out of my aircraft design short course. A note before we get going, first of all, I'm not a judge, I'm not a contest official. They asked me to give this talk, and I'm happy to do it, happy to support this project, but I'm not directly involved. And I also must say that if there's anything in my presentation that is incorrect compared to the official contest rules, it's the contest rules that you have to follow. So anything I say, take with a grain of salt and double check it to make sure I got it right. Anyway, I do want to talk about some of this stuff. I put together a little configuration, which is shown here. Excuse me, just for fun, though. This isn't my idea of an entry. I didn't do any analysis. It's just for fun. And some of you might have already recognized it. I'll let you figure out whether you can recognize it as we go through the presentation. But let me, oops, for some reason it's not working. There we go. I'll give you a little bit of a hint. Maybe that'll help you recognize it. Okay, things I want to talk about, really 5 things. First of all, I want to run through the rules as I see it from a designer's point of view, just particular things that caught my eye that you might pay extra attention to. You've already had a presentation on the rules, so I'm not trying to be exhaustive here. I'll spend just a little bit of time on it, but a couple of things kind of caught my eye. I want to talk about the design process and sizing, and many of you, those of you that are working aeronautical engineers already know this stuff. Other people are coming at this project from different backgrounds, and I'm really talking to those people, trying to give them a little bit of an overview of how we do aircraft sizing and how we go through a design process. Oops, I actually didn't mean to press that so soon. I want to talk a little bit about thrust and propellers and ducted fans. I won't talk about jets because I don't think anybody is looking at jets for this thing. Although my little illustration actually originally had jets, and I put props on it, if that helps you recognize it even better. I do want to talk also about electric aircraft analysis and sizing. Almost certainly the designs will be electric, although if somebody has a non-electric airplane idea that works, that would be fun to see also. But I'll talk about electric aircraft and show some of the equations that we use for that. And then let me talk a little bit about vertical flight, which this obviously needs. And I'll talk about some of the experiences of people designing aircraft with vertical flight, which is always tough. It's a very tough thing. Okay, so let me just start talking a little bit about the overall design requirements. The basic goal is very simple. We want to save lives, and that's always a good goal. So it's some kind of a rescue vehicle. It's a flying stretcher. It's a one-man robotic ambulance, flying ambulance. It's something along those lines. This thing has to get in there, and somehow a person has to be taken out to safety in some manner. And you might also take people in there. You might say take rescue people in there, and then they'll stabilize, say, somebody who's injured or something, and put them in this thing and push a button, and it flies them to the nearest hospital. That's the basic idea. There are areas in the country that have what's called an ambulance desert, where if you're badly injured, you've got a long wait, up to half an hour, and of course, some places a very long wait. But we're actually pretty good in most countries these days. Excuse me. With wait times of 5-6 minutes or so, which is really pretty impressive. I'm not sure that works here in Los Angeles if they get stuck in traffic on the 405. So I might be in an ambulance desert myself, living here near LAX. Anyway, that's basically what we're trying to do. And of course, the obvious comparator is helicopters. And I spend my summers in Sweden on an island, and the only access in an emergency is helicopters. So I often get an air show with helicopters flying right over my house there on their way to pick somebody up. And once they had to pick up the next door neighbor, an old fellow who had some heart trouble. At 3 o'clock in the morning, they were hovering over my house at something like the 20-meter altitude, very, very low, blowing all the leaves all around and waking us up, and lights everywhere. And they were looking for a place to land, and they literally couldn't do it. And I ran out in my pajamas and made arm motions and waved them in the direction of a place where I knew there was a parking lot where they could probably land. So anyway, it sure would have been nice if they had some way of getting into that area. Okay, this is one of the scenarios, trying to bring somebody in from under a forest canopy. And that, of course, was the problem over in Sweden. So you have somebody who needs help, and you have some kind of a VTOL vehicle, but you have trees in the way. So you want something that can go around like that and hopefully land near the person, not on top of them. But that's kind of the basic idea. Drowning victims, douse a nascent wildfire. I had to look that one up myself, maybe you too. Not a word we always use, but that's what it means. So a wildfire that's in the process of growing. So that's the kind of things that we're talking about. I think you all know that. There's 3 missions defined in the requirements, and you have to do a good job of all of them. And you've seen this picture out of the requirements, and I'm sure you've been going through that probably far more than I have. So you have to design in response to those missions. You probably saw this also, but the ground vehicle is part of the whole competition, and coming out of the ground vehicle and setting this thing up for flight is a part of the competition. So it's not just the flying machine. Okay, design process and sizing. I did show this chart last year. I don't know if any of you were looking at it, but this is kind of how we do these things. We start with objectives, missions, and design requirements. And we also gather a whole lot of information. Trying to see, let me see if I can get a pointer going here. Yeah. Okay, so we also have a lot of information gathering that we have to do before we can seriously start designing. Then we start designing, we look at concept sketches, we make some calculations. It might be just pure statistics. It might even be a smart person who says, well, it's going to weigh about this much. Or we can do some math, which maybe is a better idea. But somehow we come up with an estimate of the vehicle weight, and that includes the actual mission sizing. It includes we calculate the thrust to weight required, the power required from that. TLAR, that's an acronym for that looks about right. And if you have somebody very experienced on the team, sometimes it's better just to start with something that looks about right. And then once you have an actual design layout, even if it's wrong, you can analyze that and optimize it. So the next step that we go then is to actually get an initial design layout. So whatever design we think will work. In fact, it's a good idea to have 4 or 5 different designs when you start out. Don't start out thinking, I know what the right answer is. Start out thinking, well, I'm not sure what the right answer is. Let me look at 3 or 4 options, maybe 5, maybe 6. So this is an actual scaled layout, properly scaled. These days, it's always in a CAD system, always in full scale, but all the parts are the right actual size. And you need the major parts. You need the major internal parts, the propulsion, the payload, which is our mannequin for this particular contest, major components, if you're using electric, then batteries and motor controllers, the motors themselves, things like that. So you have to have the major components and have those in some kind of an actual proper layout with the wing the right size and tails the right size, assuming you're using wings and tails. Propellers the right size, ducts the right, ducted fans, whatever you're using has to be the right size. To do that, we use various design tools, some kind of a computer-aided design program. Once you get a layout, you'll probably use some kind of either computational fluid dynamics or at least some kind of aerodynamic calculation tool. We sort of call everything CFD these days, but there's a lot of good tools still, like FlightStream that aren't actual CFD, but they give some good answers. Structural finite element, things like that. You also need to input your team skills, and hopefully you've got some people with skill. And if not, hopefully you've got some people that can learn from history and read and find out what's worked before and what doesn't work. Don't be limited by what's worked before, but don't be ignorant of it either. And then from that, you come up with a final concept, you redesign it, do a final passive analysis and that sort of thing, and build it and test it. And of course, you need to have a fabrication shop. So during the design process, you have to have a pretty good idea of what you can make. It doesn't do any good to come up with the very best design ever if your team cannot make it in the time allocated. So you need to be pretty careful of that and have a good idea of what you can make. So you might prefer to use all composites, but you might not have an ability to make it, but you can buy some sheet metal tools and make it out of sheet metal. Okay, you know, that's going to drive your answer. Find that out early in the project, not towards the end. And of course, you got to put a lot of money and you got to put a lot of time in it. So that's basically kind of a design process that could be applicable to really any type of aircraft, but certainly this one. Okay, I want to talk about sizing. People who aren't in the aircraft business or have never done it before have the idea that you draw something really cool looking and then you calculate how far it goes, how long it flies. And you can try that if you want, you might get lucky. You can try that and then plan on iterating 4 or 5 times. But another thing you can do is to start with some fairly simple math that'll tell you about what the aircraft should weigh to do the design mission. Now, it's doubtful that very many of you are going to look to a fuel burning option, but if you do, this is directly appropriate. But even if you're going to be using an electric option for your propulsion, let's walk through this because I can show the sizing method and then I can show how it's different for electric. And you'll go, oh, okay, that's easy. You make this small change. So for a fuel burning aircraft, we start out with a very simple equation. The takeoff gross weight W0 is the crew weight plus the payload plus the weight of the fuel plus the empty weight. And to get an easy equation we can solve, we assume that the fuel weight and the empty weight can both be expressed as fractions. So there's a fuel fraction, WF over W0 times the takeoff gross weight, that gives you the fuel. Empty weight fraction times the takeoff gross weight gives you the empty weight. Okay, so that makes a simple equation and it's now easy to solve. I just move stuff over and divide, and I wind up with an equation that's the takeoff gross weight is the weight of the crew plus payload, whatever you're carrying, divided by 1 minus the fuel fraction minus the empty weight fraction. When we talk about electric aircraft, it'll look just like this, but that fuel fraction term will be replaced with a battery fraction term. So hang on for that, we're going to talk about it. Okay, so we have a simple equation here. Obviously, the crew and payload are the requirements. It's what we're asked to carry. I believe it's 125 pounds. And I don't know if you're going to insist on any additional, some bandages or something, or a heart defibrillator, whatever you're going to carry in addition has to be part of that. In the denominator, it's just 1 minus the fuel fraction minus the empty weight fraction. And if we look at typical numbers, a fuel fraction is typically about 30%, and an empty weight fraction is typically about 50%. So the denominator becomes 1 minus 0.3 minus 0.5, or the denominator is 0.2. So the equation is the weight of what I'm carrying divided by 0.2. That's the same as the weight of what I'm carrying times 5. And that becomes my sizing equation. So if I can estimate this fuel fraction and empty weight fraction, and I know what I have to carry, I just multiply it by 5. So that's, a very simple method. This is a pretty good method. It doesn't include everything. I won't go into the details. Come take my 5-day aircraft design short course and we'll beat this to death and subdue it. But at a top level, this is not bad. All right, so where do I get the fuel fraction? Where do I get the empty weight fraction? Well, the empty weight fraction is primarily found from empirical methods, basically. Before you've drawn the airplane, certainly, you can't add up the weights of the parts. You haven't even drawn them yet. So this is common history here, where we have a takeoff gross weight on the horizontal axis. and on the vertical axis is the empty weight fraction, the thing we're looking for. And you get data on a lot of similar airplanes and you plot them. And it always looks like this. You always get lines that get smaller as you go to the right for a couple of reasons. There's something called minimum gauge structure that impacts this. But the biggest thing that impacts this is that there's a lot of fixed weight items that don't have to scale. They don't have to get bigger if the airplane has to grow to get more range. So if you've got a pilot sitting there in a seat and you find that the airplane has to grow, the seat doesn't have to get heavier. The avionics don't have to get heavier. The radar doesn't have to get heavier. The engine does have to get heavier. The structure has to get heavier. So, the combined effect looks like this, that you do get basically a straight line on empty weight fraction, but it does descend. Now, for a vehicle like this one, you don't have lots of statistics. You're probably drawing something that doesn't look like anybody's airplane in history before. So in that case, there's a couple of things. One of them is that, well, first of all, you're going to have to guess for that initial sizing. You'll have to guess an empty weight fraction. I'm sorry, but if there's no history that goes before, then the only history is what's in your mind. So try to guess something that sounds reasonable. Look at this chart. Don't assume that you're 10 times smarter than anybody who lived before. You're not going to be that far off from these sorts of numbers. And then when you've actually drawn the airplane, you can actually do the calculation of the components and peg a point on this chart and use that basically to come up with a historical relationship. Okay, so that's empty weight fraction. What about the fuel fraction? Well, the fuel fraction is found by going through the mission and finding how the weight of the airplane changes through each part of the mission. And again, we do this in the 5-day design class. Let me skip the details and just kind of jump to the cruise weight and the loiter weight, which are, which are typical. There's all sorts of different mission segments, and you can find out about those later, but I just want to give the flavor of it. Anyway, when it comes to the cruise weight, we're looking for how the weight of the airplane changes. So we have some ratio of the weight before the cruise divided by, the weight after the cruise in the numerator divided by the weight before the cruise in the denominator. And we find this equation by going back to an old equation called the Breguet range equation. This was derived about 100 years ago, and it gives you the range if you know the velocity, the engine's fuel consumption, that's a specific fuel consumption, the lift to drag ratio of your airplane in forward flight, and now a log of the weight ratio, how the weight changes during that cruising portion. And we simply solve for that weight ratio. That's where this equation comes from. So we can find that weight ratio, and all we need to know is the range, this engine characteristic, specific fuel consumption, velocity, and lift to drag ratio. And of course, there's a lot more that goes into this, and how you get all those is another story, but we'll skip that for now. But that's basically how this all works. There's a few caveats when you're doing the calculation. Make sure you're using consistent units. And if you're using metric units, make sure that you take into account the difference between mass and weight, of course, which is a force. We often get those confused when we're talking in metric. You shouldn't, because metric is better. It's in the British imperial units where you have pounds force and pounds mass. The confusion in metrics is you have to make sure you put in that 9.8 factor in the right place. Okay, now notice that this cruise Breguet range equation is found by integrating the change in vehicle weight. When we get to electric aircraft, the aircraft weight doesn't change, so you can't use this equation. And that's the big difference. But otherwise, it actually looks very similar to this method. So that's the basic sizing process. Let me talk now a little bit about thrust, propellers, ducted fans, and things like this. And by the way, I don't know if dropping down the payload on a string is a good idea or a bad idea. I know there's one company doing it for packages, but I was just having fun with my RDS design software and thought I would add that as one of your little eye candy pictures. I'm not recommending that, but it does look cool, doesn't it? Okay, so thrust. Thrust matching, we're trying to find the thrust required in flight. And for a normal aircraft, there's cruise and climb, which typically are the worst case. For a vertical takeoff aircraft, you also have the thrust to weight required for vertical flight. So in cruise, very nice equation, a lot of people don't realize, but if you think about it, thrust equals drag in cruise and lift equals weight, and I can combine those two equations. And I get a very interesting result, which is the thrust to weight required in cruise is 1 over the lift to drag ratio required in cruise. And you get the L over D from a very detailed aerodynamic analysis, but there's also a rather simple method. I didn't bring it today because I just don't have that much time. But if you go to my book or my short course, you'll find this very simple method of estimating lift to drag ratio in cruise. And once you know that, you know the required thrust to weight in cruise. For climb, you have to add the component of the aircraft weight vector in the thrust direction. So you make a little vector diagram, a little picture of an airplane, and you find that the thrust now equals the drag plus the weight times the sine of the climb path angle. And that same vector diagram shows you that the wing now does not have to lift the full weight of the airplane because the thrust is lifting a little bit of the weight. So the lift is only the weight times the cosine of the climb path angle. And if you combine those, you get a neat result. The thrust to weight in climb is 1 over the lift to drag ratio in climb, which looks a whole lot like my cruise equation. But I have to add to that the vertical velocity divided by the aircraft velocity. So that's actually quite easy to do. And you can find the thrust to weight required to climb at whatever vertical velocity you specify. In vertical flight now, it's pretty obvious thrust has to equal weight. You also need a vertical controllability. Helicopters require 1.05 Gs. So you need enough extra thrust to go up at a 1.05 G load factor. You also have downwash, which is the air from whatever you use for vertical flight blowing down on the vehicle. Even a jet, if used for vertical flight like a Harrier or a F-35, there's entrainment. So air around the jet exhaust gets pulled down and actually pushes down on the vehicle. So you need to take that into account. For jet-powered vehicles, a number around 1.03 is normally about right. It can go up to something like 1.05 for helicopters or even more. For a vehicle you're likely to be looking at, I'd be comfortable using 1.04, but it depends very much on the configuration. If you have propellers and they're far away from the fuselage, far away from the wing, then you probably don't get very much. It might be 1.02 or even 1.01 maybe, probably 1.02. But if your propellers, for example, vertical lift propellers, if they overlap the wing significantly, then you've got quite a downforce on the wing. It might even be more than the helicopter 1.05. So this is something that needs to go into your analysis. You need to think about this a lot. Okay, I'll talk about propellers. There's a common misconception or a common misstatement that a propeller turns power into thrust. That's ridiculous. The units are wrong. It's apples to oranges. Instead, a propeller turns power into power, and it turns it from the shaft power of your motor to thrust power, which is always force times velocity. And we don't do a perfect job, so there's some losses as we do that. So we've got this invented term eta sub p, which is basically just a loss factor. It says my propeller throws away some of the power of the motor, so I get a little bit less thrust power out of that. So we solve this equation for thrust. You've all seen this before. That's where this equation comes from. It's nothing fancy. It's just pure physics of turning power into power. The obvious problem here is in the denominator, this velocity term. The faster you go, the lower the thrust. And that's why propeller-powered aircraft don't go that fast, because as they go faster, they get less thrust. Even if the efficiency is ideal, even if it's got perfect efficiency, you still lose thrust with increased velocity. But in the real world, when you get fast, especially near the speed of sound, the efficiency drops as well. So this is why propellers don't do so good when you get near the speed of sound, and you've got the combined effects. All right, so that's one part of the story. So how do we calculate that? Well, there's a bunch of historical data, test data, tons and tons of test data. So you don't have to reinvent this. So you can go into test data, and there's various charts and graphs. You have to read the chart and graph to find out how to use it. It's like a little cookbook. It says calculate one magic parameter, read off here. It's another magic parameter, solve for what you're looking for. It's not that hard. So that's what you do in forward flight. You can also, of course, write equations. There's various software you can find that does a good job. Now you can design a better propeller. You can actually do better than these kind of historical terms. If you design your own propeller and you know what you're doing, do watch out. A lot of times propeller codes wind up being a little on the optimistic side compared to what you actually get when you build it. And you have to build it perfectly, and you can't have any other factors that you didn't think of. And there's all kinds of extra losses that might not be included, nacelle blockage terms and things like that. So be careful, but typically this is how you calculate it. Now, if the velocity is zero, you have another problem, and that is that this implies that the thrust goes to infinity. Right? Go back to here. This equation, velocity 0 means thrust is infinity. That's not going to happen. So something different is going on. And basically what's happening is that the physics changes. At these very low speeds, as it says in red, the propeller is actually pulling air into itself, just like a fan sitting on your desk on a hot summer day. It pulls air into itself. So the velocity isn't ever actually 0. So this equation isn't applicable at 0 because the velocity isn't 0. So you can either use test data, and again, there's all kind of charts and graphs that show you what static thrust you get from a propeller. This is typical. It's the one I typically use. Or you can go ahead and use more complicated methods which were developed for helicopters and such, where they actually include the induced velocity effect and solve from that. A little more complicated, not necessary. Anything over about 50 knots, you're just fine with the usual forward flight equation. But if you want to go static like anything hovering, then you got trouble. Okay, ducted fans. People like ducted fans a lot. I am kind of running out of time, so I don't want to spend too much time on it. But the basic problem with ducted fans is the efficiency gain you get compared to an unducted propeller is only true if you have the same diameter. And a lot of times people forget that. They show a little ducted fan like this and they think it's going to have the same efficiency as a propeller that's this big. And that's not true. It'll have less efficiency, much less, depending on the circumstance, of course. So you have to watch out for that. Make sure you're not fooling yourself. And also in forward flight, the benefits of a ducted fan tend to go away because of the drag and other effects of the duct itself. And also you have the weight of the duct. So I'm not saying don't use ducts. I'm just saying be careful, know what you're getting into, and know what the problems are. It's difficult to manufacture and operate a ducted fan because the clearances have to be extremely tight. You're building up high pressure behind the duct. If the clearances aren't tight, a lot of the air just zips forward around the propeller, and it's a loss. So the clearances have to be very, very good, which means this has to be very well constructed, very well stabilized in its central location. I saw one guy that took a propeller and he got a plastic garbage can and cut a ring out of it and stuck it around with a huge gap and showed it to me very proudly, saying, there, I'm going to get more efficiency from that. No, you're not. No, you're not. Okay, so anyway, my opinion, in forward flight, the ducted fan, the advantage disappears by 100 knots and maybe 50 if everything is considered. Now that's for a big aircraft. If you're doing little model aircraft, there's other advantages. I won't go into it too much. Holman's book has a static thrust approximation. I don't know where he got that, but Holman's a sharp guy, so it's probably usable. All right, electric aircraft analysis and sizing. Let me talk about that and show you some of the equations and how this differs from a fuel-burning aircraft. Why do we like electric power? Well, about 20 years ago, maybe 25, I put this chart together. It was maturing fast. It's still maturing fast. It's not as far as I hope we would be by now. Most of the difference from what we hoped 20 years ago to what's happening today is in the batteries. The batteries are much better, but we were hoping for even more better. We'll get there eventually, but it's tough to really put a lot of energy into a battery without other things happening. Okay, but other than the power supply, I made this little gag cartoon here 20 years ago showing the big problem is that extension cord. But otherwise, we love electric motors. They're very reliable. They just last forever. They're very smooth. They start up. They don't worry about icing or things like that. There's a lot of good reasons for it. The motors themselves are very lightweight. They're actually very efficient. The electrical power that they get, they lose very little of it in delivering it to the shaft. Then, of course, you still have the shaft to propeller. The propeller itself loses some of that power. But the motors are very efficient at delivering power to the shaft. There's also a possibility of regenerative braking. You could possibly run those as a generator and stay high all the way until you got to your destination and then dive down and gain back the energy needed for landing. Maybe, at least the words are there. It might be possible. Okay, but the problem is the power supply. And it's another old chart here. This one comes from 2002. Hasn't changed all that much. We're looking maybe a little bit better. I've added these dotted boxes. I think we're about that much better. But you also have to really watch out when you're talking about a battery, because you'll very often see some great announcement and some startup company or some college professor has come up with a great new battery technology, and they tell you these wonderful numbers, and it's like, yay, finally, finally electric motors can compete with a tank of gasoline. And it turns out that that was for a single cell, not a fully installed battery, didn't include the casing, it didn't include whatever electronics are required. And by the time you put, oh, and it was optimistic also, by the time you put all that into an actual battery, it's, if you're lucky, an incremental improvement. We're still not seeing that great breakthrough. If we get even 500 watt hour per kilogram in the actual installed battery with everything taken into account, that'll be wonderful. And if we ever double that, that'll change the world. But as of now, it's still not really competitive. By the way, the comparison with gasoline here includes the knockdown for the internal combustion losses. So that's basically delivered shaft power coming out of a tank of gasoline, not the actual chemical content of the gasoline itself. And a tank of gasoline is far better than anything from batteries. So just watch out for this. Okay, range and sizing and actual calculations. First of all, as I said, you cannot use anything like a Breguet equation because we're not integrating a change in weight. I mean, Einstein says there's a change in weight, but not enough to integrate. We can do this backwards. As I said, you can just sort of eyeball something. You can pick a motor. Gee, I like this motor. You can calculate the weight to motor. This is like a ratio, the takeoff weight to power available. And you can compare that to history and sort of pick one from history. And this then will tell you what the weight has to be. If you've already picked the motor, you know the power, you pick this ratio, it tells you what the weight has to be. Draw an airplane from that weight, analyze it, see if you get the range you need. And if not, change it. You can do that. There's nothing wrong with that approach. Sometimes I do just that when I'm in a hurry. But you can instead do a little bit of calculation. Why not spend an hour before you start drawing an airplane? So that's what we'll talk about now, some of these equations. The basic equation that gives you the total runtime for an electric motor looks like this. It doesn't matter, none of the aircraft characteristics matter. This is a motor on a bench with a certain amount of power coming out of it. So that's the power being used right now. And it's very simple. You can derive this. It's just basically rearranging the definition of power, basically. Anyway, so the mass of the battery times the battery specific energy. So it's the watt hour per kilogram. So when you multiply these two together, you get the watt hours of that battery divided by the power used and work out the right units. You get the endurance, the runtime, except you don't get all of it because there are efficiency losses. So this term here, eta battery to shaft, is what B2S means. So it's the total efficiency. So this includes losses in the lines, the wiring. There's a little bit of loss. It comes out as heat. You probably have a motor controller. You're going to throw away a little bit of the power in the motor controller. You might have some other losses in there. Maybe there's some cooling that has to be provided, other things that might take away some of that electrical power. Okay, so when all this is done, if you get the units right, the 1,000 has to be thrown in there because of a K being used in some of the terms and not in the others. And you get the runtime in hours. Okay, so that's the basic equation. I can take that and build from it. I can actually find the endurance, the runtime from that equation, but now I'll build into the equation the power required. So here I have to tell it the power I'm going to use. With this equation, this aerodynamic term lift to drag ratio and some other things are telling me what that power setting has to be. And I combine equations and it looks like this. And notice that when I combine these equations, the power required depends on the mass, the total weight of the vehicle. And I collect terms and pull them out, and I have the mass of the battery divided by the mass of the airplane. So that's a mass ratio. And we use that. It's kind of equivalent to a fuel fraction. We use that in the sizing. I can do the same thing for level flight. I can calculate the range I get by writing down the equations that tell me how long it takes to go that far. And then I go back to this endurance equation. If I run at this power setting, I'm sorry, I said that wrong. To calculate the power setting required for cruise, and if I take the power setting required for cruise, put it in that previous equation, solve for terms, I can get the range out of that aircraft. And once again, I can collect terms and I get this ratio battery mass to vehicle mass. Okay, so this MB over M, we call a battery mass fraction, and I can turn that around and I can solve for the battery mass fraction. So here it is solved for loiter, here for cruise, here it is solved for climb, and I can solve it for other things. I can solve it for hover, or just basically solve it from the runtime equation, power setting required. So from the combination of battery mass fractions, and I can combine them together into the complete aircraft battery mass fraction. And I start with a completely different derivation, and I wind up with this equation for the takeoff gross weight. This is the sizing equation for battery-powered aircraft, and it looks just like the fuel aircraft. And it's derived in a completely different way, but it winds up looking just the same. Of course, the fuel fraction is replaced with the battery mass fraction. Here's the peculiar thing. When you go through all the equations, you realize in this case, the battery mass fraction is not the product of the individual terms, it's the sum of the individual terms. So you find a battery mass fraction required for loitering as long as you want to loiter, for cruising as far as you want to cruise, for climbing, and anything else like hovering, and you add all those together, and that gives you this battery mass fraction. So that's how you do the sizing for an electric powered aircraft. And I think I have just enough time then to go through some of the things to think about for vertical flight. So let me jump right into it. This is an old chart. This data goes back to the 1960s. I've seen it in many books. I think it goes back to a McDonnell Douglas report, but I kind of forget. I took that graph and I didn't feel like plotting all those points. So there's about 50 or 60 points. I didn't feel like plotting them all, so I put blobs around them. And that's really what we're looking for, is kind of an indication. And this is actually very, very useful. This is what you get in terms of the actual thrust based on the disk loading. It's all in British imperial units, forgive me, but you can make the conversion. So this shows you something very interesting, though, which is that if you try to use a jet for hovering, it takes about 10 times as much power, maybe more, as if you use a big rotor for hovering. So this is why jet-powered VTOL aircraft aren't even slightly efficient. You use that vertical flight capability very briefly, whereas helicopters can hover around for long periods of time. They're actually more efficient in forward flight, even helicopters, but if they have to, they can hover for a long period of time. There's one more aspect to this thing, and that is that there is an Army rule of thumb that says if you're over about 10 pounds per square foot in your disk loading, you have such a high velocity downwash that it isn't good for troops under you. So if you want to hover and have people climbing up and down, going up and down ropes, the rule of thumb was always 10, and they went over that for the V-22 quite substantially. So it's a problem with the V-22. I mean, they do it anyway, but it's a much greater downwash velocity than certainly anything that's comfortable. Okay, and if you go way to the right on that, like a tight, high-powered ducted fan, it's really going to be uncomfortable. So a big spinning rotor is a good idea if you're going to have people underneath a flying vehicle or a lot of distance, which is where that idea with the long string comes from. Various different helicopter arrangement. A single main tends to be the lightest weight and probably the most efficient. Problem with a single main rotor is right here. You've got to do something to take care of the torque of a single main. When you apply power here to rotate the rotor to the right, the nose of the vehicle goes to the left, or vice versa. And you typically will lose a lot of your shaft power spinning this little, it's a propeller, but it's in the back to provide a moment. You're going to lose something like 10, 15, 18% of your power spinning this thing. So there have been all kinds of other approaches to avoid that, coaxial, tandem, side-by-side tandem. They all try to avoid that problem, but they all have their own new problems, their own extra weights, efficiency losses, et cetera. I think the single main is the winner in the end, and the vast majority of helicopters have been single main, but there's always good reasons, good arguments for looking at one of the others. Do a trade study. Now, intermeshed also. Now, there's one called a quadcopter, which has come along more recently. It's actually very old. It goes back, I think, to the 1920s. But of course, today you see them for all the little electric powered drones, including little toys that cost 20 or 30 bucks now. It's just amazing how tiny those things are. This can be used to solve that torque problem by having them spin in opposite directions. And in fact, you can get the yaw you want from the torque, and it works like this. So basically you have these things set up so that they're spinning in the same direction, kitty corner here, the right front and the left rear, and the same thing, the right rear and the left front. And if you increase the power on this pair and reduce it on the other pair, you yaw to the left and vice versa. And obviously you get roll, pitch, and yaw by changing the amount of thrust going front, back, and then left, right. If you don't get enough yaw, which is very likely if you have a big tail in back and a wind blows you, if you don't get enough yaw from simply varying thrust diagonally as shown here, you can actually put these things at very slight angles from the front that give it even more yawing authority with some very, very slight loss in vertical thrust. So this is a very common thing that we do now. If you want redundancy, and you probably do, you can either have 8 of these things scattered around the vehicle and put them on completely separate power supplies, or you can stack them vertically, have a quadcopter where each rotor is actually 2. You have one on the top here and one on the bottom. That's also a very common arrangement. Last time I looked, somebody had a patent on that and they were enforcing it. I can't imagine that that's patentable, but you never know these days. So do watch out if you're going to start your company. Make sure that that isn't a problem. And by the way, if anybody knows if that's not a problem, let me know. Send me an email, because I haven't seen where that's been resolved. Okay, we can rewrite the equations for thrust, as I said, in a form that doesn't have a problem when you get to zero velocity. So what we have to do is take into account the velocity. And so here I have just an arbitrary chosen name. I call it V1 is the velocity right at the disk. V0 is far above, and if I'm hovering far above, it should be 0. And down below is some downwash velocity, V2. And I can go through the usual development where I'm setting the thrust and kinetic energy and equating and go through the whole thing, and I can find an efficiency and all sorts of things. The one I'm looking for is down here. I can calculate the thrust, and that's determined by that velocity induced right at the disk. And I can solve for that velocity. It sounds like a weird way of doing it. I can solve for that velocity, and that tells me what that velocity has to be for a given amount of thrust divided into a given rotor disk area. And then I can use that to calculate the power required. So I wind up getting the power required as thrust times velocity, and it looks like this. And if I'm hovering, my thrust has to be about equal to my weight. As I said, it's actually got to be a little bit higher, so we'll take that into account later. But thrust has to be about equal to weight. So this is the disk loading of the propeller. This is the horizontal axis on that graph I showed a couple of minutes ago. So we can now calculate the ideal thrust. This very simplified analysis doesn't take a lot of things into account, but it's a very common classical analysis. And typically you get 15 to 20% less thrust. 17% is a good approximation, less thrust than predicted by this method. So just knock it down or increase the power required a little bit. So that'll tell you how much power is required for hover. Like I said, add to it to take into account that 17%, add to it for the downwash that we talked about, and add 5% more for vertical acceleration. It doesn't do this helicopter any good to hover. He wants to go up. So you need 0.05 G extra thrust to go up. In forward flight, you can actually treat a rotor or a disc or some kind of a helicopter vehicle. You can treat it like an airplane. If you're moving fairly fast forward, then the disc of the rotor actually acts like a weird wing. There's oncoming air. The air is turned downward. There's a downwash behind it. There's a lift distribution across the rotor disc. If you kind of squint, it's a round wing. So you can actually apply the same methods that we use, including Oswald's efficiency factor. The aspect ratio, do the math, it's 4 divided by pi. And typically your equivalent Oswald efficiency is pretty terrible. It might be around 0.6 to 0.7. So you can use, I don't know, I'd use 0.65 maybe as your Oswald efficiency factor. And that'll tell you what the drag is in forward flight, and you can calculate the power required. Then you also have to assume some losses equivalent to the propeller losses to get thrust in forward flight. And it turns out the rotor acts sort of like a forward-facing propeller. The forward component acts a little bit like a propeller with an efficiency, and it's also something like 0.7 or so. So you can actually use simple airplane equations to calculate power required in forward flight, add some more losses if you have a tail rotor, and any mechanical efficiency losses you might have. but it's a very crude way of doing it. Of course, hopefully you're going to have some smart people with smart tools do a better job. But in that early knock out some numbers phase, this is pretty good. All right, well, that is the end of the material that I was going to show, and very happy to take any questions now that you might have.
Thank you so much, Dan. So much information. That we have a few questions coming in. As a reminder, please use the Q&A function in the Zoom webinar to post your questions. One question we have, Dan, is do you have an update or can you share the current status of LIS batteries?
I'm not the best person to ask on that. Anything you ask me, I would just get from somebody else. So the projects that I'm on, I'm doing the vehicle layout and the analysis, and then we have experts in the fields of batteries that are going through all those. And any numbers I have now would be somebody else's proprietary information. So I'll have to pass on that question for two reasons. I'm not the guy to answer it, and anything I know is proprietary to somebody else. Sorry.
Thank you. What would be the procedure to find out the theoretical limit for lift by drag ratio for subsonic and supersonic aircrafts? They're saying analogous to the Carnot efficiency for heat engines.
I'm not comfortable with the sort of theoretical analysis that tries to find limitations and such like that. I know other people do, but I don't. I sort of stick to the configuration, to the concept itself. That's why I named my book A Conceptual Approach. I want to focus on the concept. So I want to do an actual design layout as best I can, and then calculate the aerodynamic efficiency from that actual layout. So again, that's something I just have never messed with. And if other people want to do that, it would make for interesting reading. But I'm not gonna look into that. Sorry. That's
what do you think of cyclocopter systems?
Oh, those are the ones with the thing rotating this way, I think. It looks fascinating. You know, the physics is there. And it has some advantages. I suspect that by the time you actually get the mechanism working, I think the actual weight of all the mechanisms is going to invalidate any benefit to it. But I'd be delighted if somebody proved me wrong on that. But yeah, to me, the aerodynamics looks good. It looks well thought out. I don't see a real problem there. It's just a matter of mechanical design, getting the weight down in something spinning like that, taking into account gyroscopic forces, failure modes, and all that kind of stuff. So I would love to see somebody continue to pursue that. It's a cool concept.
What is the current approximation of the thrust to power ratio that VTOL aircraft can achieve?
I showed an equation that was thrust for vertical takeoff of a ducted fan for a propeller type thing. You really have to calculate it. It depends very much on the disk loading. I showed that in the equation. You can use that simplified method. It's a pretty good method. But of course, much better methods are available, sort of computational type solutions that solve for the static thrust of propellers. I don't have there is a theoretical limitation. I'm trying to think of the name of the equation. I programmed it, but that was years ago. It's buried in my RDS program, a theoretical limitation on thrust. But basically, there's so many factors involved that I don't see a way of coming up with a simple the top level number other than this momentum method that I showed before.
Can you share a few words about the hydrogen element in the competition? Any thoughts?
If the question means the use of hydrogen as the fuel supply or the power supply, well, it's certainly an option for the electrical power fuel cells. Refresh my memory, it wasn't specified, was it, in the requirements? Are they required?
No, it is not.
Okay, so it's an option for fuel cells. I showed a picture in the beginning of a little airplane that was sort of painted red-orange, and it had an extension cord coming out. That was actually my design for a hydrogen fuel cell contract. We were looking at an airplane with a hydrogen fuel cell. It was funded by NASA Glenn a while back. So I did look at the hydrogen fuel cells, and it's one of those options that looks really quite good. I don't know what's going to be the winner in the end, but it certainly is a very good option, hydrogen fuel cells. You can also use hydrogen in an internal combustion engine, and that also looks good. The hydrogen always has problems of distribution. Where do you get it? You have to make it. You don't dig hydrogen out of the ground. You have to use lots of electrical power to create hydrogen. So somebody has to build ground facilities that can make lots of hydrogen, and then you have to get it to the vehicle. So those sorts of problems are challenging. But yeah, it's a very, very valid option. One of the things people are looking at.
How do you go about airfoil selection?
Well, it totally depends on the requirements of the project. You have to look for airfoils that have the best aerodynamics, or even design your own. There are some good airfoil design codes that, if you know how to use them, it's a good option. I'd be cautious if you've never done it before, doing it for the first time on your project. But you can get pretty close by selecting an airfoil. Basically, you're looking for an airfoil with a good lift to drag ratio at the lift coefficient that you'll be flying at. And you're also looking for an airfoil with a good maximum lift coefficient, hopefully not too much pitching moment. You don't want it to over twist your wing. And also you want to take into account structure and fabrication. So there's some wonderful airfoils, especially for low speed flight, low Reynolds number flight. There's wonderful airfoils that are quite thin and very cambered towards the back. And I'd have a hard time building that. So I've never used those on projects just because of fabrication. So anyway, yeah, you need to compare the available airfoils with your actual operating conditions, or design your own to those operating conditions.
So the competition is focused on safety, this project. Do you feel redundancy with 6 to 8 propellers is worth the weight cost?
Well, I think you have to have redundancy for something like this. There'd be nothing worse than a headline where somebody was rescued from a fire and dropped back into the fire because of some failure. So at least if I were doing it, I would want to have complete system redundancy all the way through, basically like 2 airplanes smushed together into one, such that it could fly or safely get away from danger and land, even if one system failed. Now, you could do redundancy at a component level, but then you're controlling it by the same system. So then if your controlling system has trouble, then you could lose the vehicle. The counter against that is it is going to be heavier, and you can do analyses that shows the likelihood of system failure. And if you get the likelihood of system failure down to less than the likelihood when you step into an elevator in a high-rise building, maybe people would accept it. So it's a little bit of a marketing decision. It's kind of a gut check for the design team as to whether you want to try to be accepted based on a system reliability analysis, or whether you just want to go pure redundancy all the way through. I guess I tend to be a little more conservative. I'd probably go pure redundancy. But if somebody else did it the other way with system redundancy, I'd probably go, oh, okay, I mean, I'd fly in it, but I jump out of airplanes and fly aerobatics. So well, a lot of people don't want to do things like that.
Do you see any advantages of tilt rotorcraft over other transitional aircraft? For example, a quadcopter having a pull-push propeller and wings.
Yeah, that's the big debate going on right now, and it's being done with hundreds of millions of dollars of other people's money. So we'll see who the winners are in the end. But the options are to have rotors that are always pointing upwards and shut them off for forward flight, or to have rotors that are pointing upwards and pivot them so they point forward for forward flight. And I tend to be on the side of let's keep them pointing up all the time, because then transition is just feeding power to a different source. But I sure see the arguments the other way. I'm not at all convinced that I'm right. And if I were starting a company to do one of those, I'd look at both very seriously for a very long time before I made my decision. When you tilt it forward, of course, the argument is that you're not putting in another motor and propeller. You don't have their weight, you don't have their drag. And all you have to do is add a pivoting mechanism, which you've all seen these things at the front end of the Archer and the various other vertical takeoff. And they look like a little, kind of like a little 4-bar link thing, like the mechanisms that open your cabinet doors in your kitchen. And they don't look real simple and clean, and they look like the load paths are terrible, but it's just mechanical engineering. You just get a mechanical engineer to design it, and the mechanical engineer will tell you how thick and how heavy the parts have to be to get to the point where, you know, the likelihood of that part failing becomes extremely small. And then all you're doing is adding the likelihood of the actuator failing also. And you buy actuators that have high reliability, and maybe that's good enough. Anyway, but if you go that approach by pivoting either at the nacelle or even the entire wing, then you avoid the extra weight of the redundant, you know, the multiple components. Yeah, it's a good argument. I'm very eager to see who wins in the end.
Dan, we have an interesting question. Back in the 80s, there were some concepts with scimitar-shaped rotors. Does that offer advantages in certain flight? And for clarification, they meant it's like a sword, an interesting design that was used for a conceptual attack helicopter back in the 1980s.
Yeah, the scimitar shape, it's a curvature going to the rear out at the tip of a propeller or rotor. It's still being looked at and being used. And it's basically a way of reducing noise and hopefully increasing efficiency a little bit. What it basically does is it moves the tip vortex out a little bit. And it also basically, well, you get less of a chopping out at the tip that is one of the noise generators. So it actually gives a little bit more efficiency, and it also reduces noise. And they definitely work. There's no question about it. And they're being put on helicopters and forward flight airplanes as well. In fact, I just saw one being installed literally about 2 months ago. The airplane that I fly, which is a Sling 2 from South Africa, they are testing a Scimitar propeller because they're getting such noise complaints from Torrance Airport, which is where I fly. So it's definitely a good technology. There's obviously problems. Nothing is easy. There's issues of those little end pieces coming off, and then they would transform from scimitars into those ninja throwing stars. And who knows how far they would go, but they would definitely kill anybody they hit. So those are some problems. But yeah, it's a good idea and very closely related to the similar wingtips that you see on airplanes like the 787.
Why are variable pitch rotors not used in ducts or shrouds?
Why are variable pitch rotors not used in ducts? They could be, and you might get a little bit more efficiency. But when you have a duct properly designed, you can change the cross-section area of the duct from the intake area to the actual location of the rotor, fan, whatever you call it. And you can set it at a certain speed to be efficient. Basically, you can set it so that it slows the air down and feeds it to the propeller at the speed it desires. Yeah, I guess that's all I can think of to say on that subject. You certainly could do it, but you can get very good efficiency without it. I think that's probably the real answer, that by controlling the duct area, you get good efficiency without it. Oh, also by controlling the duct lip radius. So you can get the air to go around the corner into the duct much better than you can with a propeller out in the free stream. So that lets you feed the air to the fan at the speed it wants, rather than at whatever speed you're flying at.
So we are at time, so we're just going to take just one or two more questions. Do you have any opinions on the toroidal props? I don't know if I'm saying that correctly.
Somebody putting toroidal, I think it's toroidal.
Mm-hmm.
Boy, loops. If somebody's putting loops out of the tip of propeller, that's another thing that's been used as a winglet, where you have a winglet that loops all the way around and comes back and reconnects with the wing. And they claim some efficiency advantage. I assume they're claiming the same for the propeller. I haven't actually seen that one. That really sounds like something I'd be scared would come off and fly around and hit people. But I haven't seen that. So I guess I'll stop there.
Okay. Do you have any recommendations on flying a ductless aircraft in urban conditions?
Ductless? You mean, in other words, exposed propellers rather than ducts? Well, yeah, that's one of the reasons for using a duct. It's a reason they put a shroud on the tail rotor of some helicopters, is to just make it a little bit safer. You're just less likely to hit that tip. Yeah, that's an advantage right there that can be claimed. But all the things I said about ducts are still true, and it's going to add a lot of weight. So you better hope you get a big thrust advantage from that. And in forward flight, if you don't tilt the rotors, then it's really difficult. Forward flight with a tipped duct is very inefficient. So watch out for that one. But it would definitely be safer, and it would also be perceived as safer. And sometimes the perception is even more important than the actuality. So there's definitely an advantage for safety there if you put a duct around, some kind of a ring around the propeller you have.
How many pounds of thrust should a fan produce for each horsepower used?
I gave an equation, so I think that's the answer to that. I don't know off the top of my head, but if you look at the equation, it'll give you that for various conditions.
Great, thank you. Um, are the equations of electric aircraft range, consumption, etc., useful for multicopter which has no wings?
Um, yeah, no, well, da, 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 da. You could use them for a first pass analysis using that helicopter approximation where I said you can pretend that a helicopter rotor is a weird wing and use those Oswald efficiency factors. That'll get you an answer that's kind of about right, better than just a guess on your own part. So you could use that for some very early calculations. But later, you're going to have to get a much more detailed calculation for the rotor in forward flight. Now, for something like this, where you're building and flying, maybe you don't care that much. Maybe you just use that approximation and call it good enough for now. But if you're doing this as a real project and funded properly, then you'd want to get much more detailed calculations.
Do you have any thoughts on the best design software for starters, freeware, and commercial?
Well, the best design software is the one I wrote. I, I have to say that, but I actually think it's true. There's a student version of that. It's very good for conceptual design type work, but it's not good for getting into detailed design and part design. And for those, there's a lot of commercial codes. I won't list out the names. You all know the names of the various commercial codes. They're all reasonably good. There's other conceptual design codes. NASA has put out something for conceptual design, which still annoys me because I thought they weren't supposed to compete with private people, but they've done it and it's free. So certainly you might want to take that rather than buy my own software. And let's see, I guess my old friend Jan Roscom, he's passed away now, but his company DAR Corp has their own AAA software, which is in the same area as my RDS software. So those are some of the ones you could point you to.
And then finally, Dan, last question that we'll take right now is your thoughts on ionic thrust.
Ionic thrust. I think they're talking about the one where you have an electrical grid, you have a cathode and an anode. If that's the one we're talking about, you supply electrical power to it, and as the electrons go from one to another, they grab a little bit of the air. If that's the one we're talking about, I remember reading about that when I was a little kid. I was a nerd. I read all the science magazines that I could. And I remember seeing that it was working way back then. This was in the 60s. And the only problem, of course, was the power supply. It had a huge electrical cord supplying power to it, but it was actually flying around a hangar. And I think the same thing is true now. I believe the power required is so huge that it can't possibly compete with any kind of a fan or rotor or ducted fan. I think that's the case. Otherwise, it's really cool. It's completely silent, no moving parts. Very cool.
Great. Thank you so much for spending so much time with us, Dan, and for your incredible presentation. As a reminder, we encourage all the participants to please join us at herox.com/GoAERO if you have not done so already, to make sure that you can register for the competition and that you can be made aware of all of the amazing lectures that we have. We do actually have another one coming up tomorrow as well. A recording of Dan's lecture will also be made available on HeroX.com, so please be sure to register so that you can be made aware when the recording is posted. Please use the forum to post any questions that you might have following this lecture, and we look forward to Dan's continued support and participation throughout the competition. Thank you so much. Take care. Bye-bye, everyone.
Bye, everyone.